We proceed with the next speaker, Francesco Pio Ramunno. The presentation's title is Modeling Solar Images from SDO AIA with Denoising Diffusion Models. So I'm going to give you a 5-minute warning, okay?
Okay.
It's like this.
Welcome everyone. My name is Francesco Pio Ramunno, and today I'm going to speak about modeling solar images coming from the SDO telescope using the denoising diffusion probabilistic models. The idea of this project actually is to use, as you could see from titles, generative models, but denoising diffusion models specifically, to produce images of the sun with a specific amount of activity on top of it. So not kind of vague images of the sun, but trying to control what we want to replicate on its surface. The reason why we want to do this is because we have a lot of very rare events from a physical point of view, such as like M or X flares, and we would like to solve the problem of the unbalanced data set that we have, so that having more data, we can use it for a lot of kind of tasks, both physical tasks or other machine learning tasks, like trying to improve the classifier accuracy on this data and things like this. Here you have an overview of the generated images. So we are able to generate, for example, A-class images. These are all generated. These are not true data. And now I will show you how we can arrive to this point. First of all, the data sources that we took in consideration are the following. So we are using the SDO version 2, which is a subset of the SDO data that has been already preprocessed for all machine learning studies. Then we are using the ghost sensor for the soft X-ray measurements, and the HELIOPHYSICS image knowledge base to retrieve the flaring informations. The flowchart that you can see here is the data preprocessing techniques. You can read it from top to bottom. So first of all, we took all the images from 2011 to 2019 from the SDO version 2. Specifically for this project, we are focusing on 171 angstrom band. Then we go to the HELIOPHYSICS events knowledge base, and we do select all the flares from 2011 up to 2019. And we do the same for ghosts, such a way that we can retrieve the X-ray measurements. Then we correlate the HEC and ghost dataset in such a way that for each flaring event, we can associate also the X-ray measurements from ghosts. And so then we can label the SDO images that we have in the first object. We pass from 1 million images to up to 22,000. That's because also of one of the limitations of the SDO version 2, which is the time delay limitation, since that it does not follow the time cadence of SDO telescope, which is 12 seconds, but it is 6 minutes every image. Okay, so let's dig into the experiments itself. Denoising diffusion probabilistic models are cutting edge in kind of generative models area of machine learning. We can summarize them in 3 bullet points. The first one is the forward process, where we are not training anything. This is a fixed Markov chain in which step by step we add Gaussian noise to our image in such a way that, so that's why we have a progetoria of Q, which is the distribution, and the distribution is a Gaussian sampling from a Gaussian distribution with this characteristic, where beta T is called variance schedule, and capital T is our step, so it's the number of steps that we use to noise it, and from T that tends to infinity, beta T tends to 1, and 1 minus beta T, and the square root of it tends to 0, of course, meaning that at the end of all this process, we have a full Gaussian noise of mean 0 and standard deviation 1. Then we have the reverse process, which is actually where the model acts. And in this case, we are trying to predict, again, step by step, all the noises that we added in such a way that then we can remove it and obtain the image. In this case, where we are working on the mean and the covariance metrics, so we are predicting them in this way. And at the end, we have the classifier free guidance technique, which is the technique that it's used to kind of guide our generation. Because as I said at the beginning, the most important part of this project is not to generate images, SDO images of the sun, but to guide the generation and say, for example, generate me an image of the sun with an X flare. That's the idea of the whole process. And you can see in equation 3, basically how we do this. We use the label that we prepared on the data preparation part, and actually we concatenate this label inside the model, and the model that is behind it is a unit. Then we do a linear interpolation between a condition prediction of the noise, this is the noise, epsilon, and an unconditioned prediction with a particular guidance scale that is this W parameter. Here it's a sketch of how it works. We can see from x0, that's the first step, we noise it up to xt. Of course, from computational reasons, it can be infinity, of course. We are using 1000. So we are using 1000 steps to noise our data. And then again, from x capital T, we go up to the image predicting the noise and removing the noise step by step. Basically, we used an easy resolution of 64 by 64, always for computational resources, 500 epochs for each model that we trained, and the batch size of 12. We trained 3 models using the same backbone. So the backbone of the diffusion model, it's similar, while what we change is how we label our data, so how we guide the diffusion, that's the idea. We do it with discrete labels, so using the ghost classes in this case, then with continuous labels, so use directly the X-ray values emission, things like generate me an image of an X-ray emission of 10 to the power minus 5, for example. And then we use discrete labels plus the CVA embeddings. CVA embeddings is kind of a feature vector of a CVAE, which has been already pre-trained on SDO data. And this CVAE will also be our baseline. So we compare our results to this CVAE that is already pre-trained on SDO data. To show you the results, I will first introduce the metrics that we took in consideration for this project. We took in consideration the cluster metrics, which is kind of new. This is good because it helps us to determine the generated distribution. So it compares the true distribution of the data with the generated distribution of the data, understanding the completeness. So it tells us if, for example, our model is in mode collapsant, can only generate one type of the classes that we are using to train it. The cluster metrics divides into the cluster error, CE, the cluster distance, and cluster standard deviation. Then we have the FID. FID is the Frechet interception distance. Basically, it's the Frechet distance of 2 multinomial Gaussians. That's the idea. And it helps us to determine the image quality of our generated images, but also the completeness, again, of the generated dataset. And the FID in this work has been computed with CLIP and IV3 as encoders. While then we have the F1 score, because we also wanted to judge whether our labeling system was working as it should. So whether, for example, if we say to the model, generate me an image of an X flare, actually it is similar to a true image of an X flare and not, for example, to an image of a C flare. That's the idea. So that we train a classifier on true data and we test it on generated data to see if they match. That's the idea. On this table, you can see the results. You have the first column is metrics, then you have the CVAE, which is the baseline model, and then the discrete, continuous, and CVA embedding are our models, so the model that we trained. Discrete, it's the ghost labels, continuous is the X-ray emission, CVA embeddings is with the actual CVA embeddings that we input to the model itself. We can see that for benchmark values, we are using the followings. So these are how we have to understand cluster metrics, meaning that the cluster error, the lower it is, the better it is. The cluster distance and cluster standard deviation, the nearer it is to 1, the better it is. So the best model in terms of the cluster error is the discrete model, so the one with ghost labels, while in terms of cluster distance and cluster standard deviation, we have the continuous model that works best. And this also happened for FID and for FID both with CLIP and IV3. The point is that the cluster error actually is the metric inside the cluster metrics that better define what is the similarity between the generated and true distribution, and so that tells you whether your model is in mode collapse or not. Meaning that it has kind of an higher weight with respect to the cluster distance and cluster standard deviation. Thanks. While for the precision, the F1 score and so the precision and recall, we can see that actually we reach the best values with discrete models, so with A, B, C, M, and X. And we reach a 0.7 on F1 score 0.73 on precision, and 0.74 on recall. That's why, apart from the mathematical metrics, we decide that for our analysis, the discrete model is the one that works the best, and also visually speaking. Now I'm showing you a batch of 8 generated images. So these are all generated per class. So this is saying, generate me an A image of the sun, meaning the A class. While you can see that it's pretty calm in a sense. While, for example, if we say generate me an B image, the activity is increasing. A C image, still increasing. And so it is the same for M and X images. So I want to highlight that these are all generated. If you want to compare them visually with true images, you can see these are true images coming from SDO of X images in our case. And these are fake X images. So actually, also visually, we can see that they are very similar, not only in terms of the mathematical metrics that we analyzed before. Okay, to conclude our presentation, we can say that yes, it is possible to generate SDO images of the sun, but actually the most relevant part is that it is possible to control the activity that we have on the sun with this model. And we can also apply then, the idea of the project is that we can also apply the generated images in such a way that we can manage the unbalancing of the data that we have. As a future work, we also would like to test it on other deep learning tasks, such as doing image-to-image translation with the HMI magnetograms, in such a way that we can retrieve the HMI magnetograms from the generated images. We would like to solve the problem of the dataset. As I said, we have a limitation on the time delay, and also focusing, for example, only on flaring regions and generate only flaring regions and not full sun disk. Thank you for the attention, and if you have any question, I will be free to ask.
Thank you, Francesco. Thank you, Francesco. Questions or comments? One over there.
Thank you for this great talk. So in your work, you're using diffusion models, but another kind of generative models are GANs. Why did you prefer diffusion models over GANs?
Actually, from literature, diffusion models now are overperforming with respect to GANs. They are totally winning, if you want to make it on this side. And they are better in terms of diversity, of generated diversity, I mean, and also in image quality. And another reason is that they are very easy to train, in a sense, easy from user point of view, while, of course, the benefit of GAN is that they are easy in terms of computational point of view, because one of the, let's say, the cons of the diffusion model is that they are very easy. That's why we were stick with 64 by 64 images.
Actually, that was my next question. What is the increase in complexity if you would go for a 128 by 128, for example?
Theoretically, there is no limit, of course. Practically, we already went to 128, 128. We would like to, we can push up to any kind of resolution. Here I have, for example, I have a batch of back slides, or I can show you. For example, these are 128, 128 generations. You can see that it can handle a lot of more details, of course. You can see a lot of more things that you cannot infer visually, me speaking, from the others. At the moment, we are not focused a lot on generating high resolution images, but more on the other tasks. But this is not kind of a closed point.
Okay, thank you.
Thank you.
More questions or comments? One over there.
Hello, thank you for your talk. Very interesting idea to generate the images for the datasets. Since I'm working with a different phenomena, which is coronal holes, is your method, or would your method also be suited to generate images of coronal holes, for example, or of other structures on the sun?
I don't have experience on generating coronal holes, but in theory, yes. You can generate basically anything if you have a proper data set to do that, and of course also the labeling system. In this case, the reason why we could be able to control the activity is because we had labels. But yes, in theory, you can do it.
Cool, thank you.
Any more questions or comments? Any question or comment online? Nothing? So let me ask one question. I found what you mentioned, namely combining, pairing, reconstructed or as you call them, fake UV images with magnetograms. This has been, as you know, quite a bit a task in the literature, providing magnetograms to pair with UV images, particularly in the far side of the sun. But there is this big problem that, in my opinion and understanding, has not been solved so far. How to correlate, how to put together different polarities in the magnetograms, because the EUV images do not give you polarity information in the magnetograms. So I was wondering whether you have any ideas in this particular respect, because, as I mentioned, I don't think there is a concrete solution on the problem.
Well, actually, we are not still digging to the image-to-image translation problem, where we could first, because for image-to-image translation, you have first to pair for example, UV and
That's okay.
The UV and the magnetograms. So I don't have a direct answer at the moment for this. Yeah.
All right. Well, let us thank Francesco again. Thank you.